Let's get started. Thank you for joining this webinar. I'm Tetsushi Ueta at Tokushima University. I'm very happy to have this webinar with this title, subject, Locating and Controlling Chaotic Saddles. If you have some questions, please use a chat and please type the question in text. And end of the webinar, I will answer the questions. Pick up some of the question and I will answer the question. Okay, let me start the contents. Maybe you know when about the chaos. Recently, chaos are ubiquitously happen in the several physical process, including circuit and neurosciences and biologies. And chaos are referred sometimes as strange attractor. Anyway, the system itself written in the differential equation or difference equation, nonlinear differential equations or nonlinear difference equation. That's deterministic, non-statistical information or something. Only this deterministic mechanism inside of the process, but the behavior is chaotic, random behavior. Actually, I just to study on these such nonlinear system with the bifurcation theory. I just to compute some bifurcation diagram to identify the chaotic area in somewhere in the parameter plane for given circuit and systems. With some example, a bifurcation process including the chaotic situation. Firstly, if you are thinking about the nonlinear difference equation written in this form, we call this one logistic equation. And putting initial point for this x0 by repeating this equation, you have x1, x2, and so on. And for after some transition state, the point will behave like a fixed point. That means x0, x0, everlastingly here at the certain point. We call this one period of one motion. And by changing parameter, this one changed at this parameter value doubles. So you have two periodic motion here. Further parameter changing, you have period 4, period 8, and chaotic state you have. Especially parameter r equal 4, you have fully developed the chaos motion. But now, changing the perspective for this, for each bifurcation process, we call this one the period doubling bifurcation. The original fixed one motion changed to the unstable still exists here. You have two periodic stable motion here, but in parallel, you have unstable UPO, unstable periodic orbit, or periodic point. So invisible for this figure because it's unstable. After some transition state, you have stationary find the two stable periodic motion. Similarly, you have unstable two periodic points or unstable period 4 point, here, and so on. For chaotic parameter value, you have mathematically infinitely many unstable periodic orbit. Any period, unstable periodic orbit embedded in the chaos attractor. Here, another example, differential equation. It's circuitry implementation available. Third order differential equation is modeled here, and here nonlinear terms. But this kind of the very simple differential equation cause chaotic motion like this. We call this one double scroll with this parameter value. Within this chaotic motion, you have many unstable periodic orbit like them. So the more complex periodic orbit like this one almost looks like a chaos attractor itself, but a periodic, higher period, long time period, periodic orbit. But they are all of them unstable. So stationary, you have this kind of chaotic attractor, not periodic. Okay, we just try to stabilize each of them. If you pick up this UPO, we try to stabilize it. We call this controlling chaos. It seems to be a very classical problem nowadays. Firstly, OGY. Otto, Grebogy, and York proposed the linear state feedback control to stabilize the UPO. In fact, this method utilized the stable manifold we mentioned later. Embedded UPOs are all of them saddle type fixed point, periodic point. So you utilize stable manifold of them and induce the motion into the unstable periodic orbit by using the parameter perturbation, very small parameter perturbation. And chaotic wanderings itself, we utilize them to seek the UPOs. And a very tiny control input can stabilize the UPO for this OGY method. This is the very typical structure of the feedback control system. With the OGI method, we need the some kind of the hint, clue of the UPO data, UPO or UPP, unstable periodic point data, and try to making the error for this term, and as a control input, we just feedback to the original system. This is the feedback control. With this feedback control, we can stabilize the UPO embedded in the chaos. But for OGY method, it is basically a discrete type control system. OGY method itself, no targeting strategy implemented. So anyway, you have to specify a certain UPP data beforehand in other words, you have to find the unstable periodic point data beforehand, before the controlling. And other method available conventionally, delayed feedback control itself can seek the target orbit automatically, but it cannot specify the desirable target for the FC, delayed feedback control. So if the control completed, but you cannot specify the UPO, specify the specific UPO. Anyway, all of them, conventional method are very, targeting is very ad hoc. So you are very lucky. So you have, you can stabilize the UPO, but you cannot specify specific UPO. Now, the question arises, how to provide a desired target? It's very important problem. Okay, OGY-like method, OGY-like feedback method can modeled as this flowchart, signal flows. Here, original chaotic system written in the differential equation, and sampling. We just sample the state and memorize it in the memory and making a control here. Anyway, you have to find beforehand the UPO data. And control input for OGY system is the perturbation of the parameters. Another question arises, another problem arises. For OGY method, anyway, they sample the system by using a sampler or making a Poincaré mapping. So each fixed period timing, you can update the control value. During this, for example, interval, if you have some disturbances, maybe the control fails. So in this sense, the OGY-like linear feedback control is very sensitive for the initial point or setting up. So probably you have to waiting for a very long time to seek the UPO, and anyway, UPO data is also stabilized. The UPO itself is very unstable for the parameter perturbation or disturbances. Okay, now just to summarize the situation. The conventional method, anyway, you have to compute UPO beforehand, and the fixed point or periodic point, UPO data have to solved beforehand. Okay, and with this situation, the control completed. If you remain the some control inputs periodically, that means that possibly the stabilized you assume the stabilized UPO, but is this one a genuine UPO? This question arises. So today's topic, our framework, just focusing the chaotic saddles. In this sense, we mathematically problem UPOs. We just find them. Firstly, we just crop the horseshoe structure in the chaotic systems, nonlinear systems, and we just pick up the UPO data mathematically. In this structure, the UPO is existence of UPO is problem guaranteed. Just to pick one of them and try stabilized by the controller. So UPO itself is a genuine UPO embedded in the system. Once UPO located, controller replace its stability. Okay. Okay, for example, today we consistently use the Duffing equation as an example. Two-dimensional chaotic systems. And here external force. So you have period 2 pi periodic motion you can assume. And we just describe the solution with these equations. And x0 is the initial point. And we just change, how can I say, just to convert the differential equation into the difference equation by taking the Poincaré mapping, discrete mapping. So the system is the 2 pi periodic. So each 2 pi, you just sample the orbit data. Then you can convert the continuous time system into the discrete time system. So you just sampled x0, x1, x2 as the vector values, and for each transition, we just assume the map T. So you can take this equation as an sampled discrete map system. With this equation, there are several special points. Firstly, fixed point P. So you apply P for the T, you have same P. We call this one the fixed point. Similarly, if you apply the P into the T to the power of L, then you have P. We call this P L periodic point. Okay. If you have the fixed point for the discrete time system, the multipliers for them are specified. Multipliers specify the stability of the fixed point or periodic point. For two-dimensional system, you have mu and mu2 multipliers, eigenvalues. So inside of the unit circle of the complex plane, inside of the unit circle, you have stable situation. Otherwise, unstable situation. Today, we just focus on this type unstable situation. Later, we see the any unstable periodic orbit embedded in the chaos unstable saddle type. One of eigenvalue, one of multipliers is bigger than 1, and another is less than 1. For Duffing equation, this situation happened. Actually, this green curve and the red curves are periodic orbit of the Duffing equation. By sampling applying Poincaré mapping, you have this lines like this, like them. They are actually the set of points. For this Poincaré mapping, you have saddle type fixed point D. So there, with this fixed parameter values, you have two stable periodic points, S1 and S2. And depending on the initial value, you have unstable periodic point, but invisible for common sense. According to D, this saddle type fixed point, you have two eigenvectors. And related to this eigenvector, we just draw this kind of the manifold. Okay, here we just describe the manifold and the homoclinic point. Extending the eigenvectors for both forward time, and inverse time. For inverse time, it's just to making the intersections. We call this kind of intersection homoclinic points. For nonlinear system, the extension of the eigenvectors forms the manifolds. Alpha branch is the unstable manifold, and omega branch is stable manifold. Once alpha and the omega branches are crossed transversely, like H0 once, mathematically, infinitely many homoclinic points happen. In other words, near D, you have many homoclinic points. Okay, let me check the situation in the computer simulation in Duffing equation. With this parameter values, stable manifold and unstable manifold are uncrossing. No intersections. But decrease the value K, both alpha and omega branches are making intersections. Very amazingly, if you have this stable manifold or unstable manifold, if you touch once transversely, not transversely, tangent situation happen, then other bending curves touches tangentially. After this, the many intersections arise happen. For more parameter value, decrease of the parameter values. So it seems to be very complicated situation happen. So many homoclinic points generated. Okay, with this k equals 0, it means the Hamiltonian system. So many homoclinic points near the saddle D. With this situation, we just to specify the UPO with certain period and the location. Let me start the description. Okay, firstly, here comes the subtle D. Subtle D. And trace the, place the point on the stable manifold, stable eigenvector, on that stable eigenvector, and place map inverse T, then you have pictorize, trace the stable manifold. If you apply the on the unstable eigenvectors and mapping T one by one, then you can trace the unstable manifold. With this method, you can trace the manifolds. Okay, this situation happened with the intersection of the stable and unstable manifolds. Very amazingly, if you have firstly a rectangle here, by taking the Poincaré mapping just to transition state, it moves to this direction with stretching. Probably it may change the shape, very thin form, and folding, bending with the stable manifold. Then, excuse me. Firstly, you have this rectangle. Then the repeating Poincaré mapping, you have this transition. Then anyway, folded rectangle just to making the intersections like this. We call this one horseshoe structure. If one can find this horseshoe structure, it seems to be chaotic situation, mathematically. Okay, this is a schematic diagram of the horseshoe map. Here, home click point. And this actually T square and T2 square inverse. And this kind of many intersections happen. And please remind that this unstable manifold, going back to the inside of the structure, and yes, and the snap back here, and again inside of the rectangle and get back outside. But for outside, once again you just snap back here and going back to the structure again. If you have TQ, the manifolds get back like this style. Inside of anyway, this interval, not going to the outer area. Okay, for example, the Duffy equation. So for certain numerical simulation, you have this structure. So this is the enlarged area. This is most outer circumference, most outer circumference. So you just going back, go. But so return inside of anyway, this way. Most outer circumference is anyway very important. And also for unstable region, this is the most outer shape. The repeating T many curves inside of this, not exceed the most outer circumference. That means they penetrated each other outer circumstances between them. This is very important. For this case, we call this one degenerated case. Most outer circumference cannot be penetrated each other like this one. Okay, let me check the situation in the definite equation continuously. And the outer area, some snapback points you can have, you can see. So outer area is anyway invariant. You can crop the horseshoe structure properly with this figure. So most outer line here, most outer lines here and here. Anyway, the structure penetrated each other. These are very important. If you cannot take this portion like this one, the horseshoe structure not conformed. This is degenerated case. We can prove the existence of UPOs, chaotic saddles, when you have properly cropped the horseshoe structure like this. Okay, another dynamical system example. You can take the penetrated portion here and here. Most outer circumference are penetrated each other. With this situation, we just do the dynamical behavior is related with linked to the symbolic dynamical system, symbolic dynamics. Okay, firstly, we just introduced the Baker's map. Just imagine the dough. You try to make the midfield for now. Just place the dough first and 0, 1 ingredient and stretch it and fold once. So upper position we just name it name 1, and the lower portion we name it 0. Okay, and stretch once more. Upper portion still 0, still 1, and lower 0, and fold once again. Then special structure happen. So you have from the top 0, 1, 1, 0. Not to 0, 1, 0, 1, not to 1, 0, 1, 0. 0, 1, 1, 0. And stretch once more and fold once more. You have 0, 1, 1, 0, 0, 1, 1, 0. Like this situation, repeat the situation. You have midfield structure like this. But numbers compose a very special structure. We call this one Baker's mapping. It's make a gray code. Okay. Now mathematically define the situation. Okay, firstly, rectangle ABCD here, original square. And once you just map by T, it's corresponding to the stretching and the folding. Then you have this folded area. This one actually horseshoe map, horseshoe shape. Then lower portion, we name this one 0. In the upper portion, we name it 1. And repeating the mapping, stretch and the folding, then you have this situation happen. 0, 1, 1, 0. So we just record the history. Now you have one situation, the upper portion, but for upper portion, you have once a 0 situation. This one may have the history 1, 1. Okay, this kind of the trees explain the history of the stretching and the folding. For T square, T cube, you have 3-bit history, and all of them not duplicated. One by one, you just distinguish. Okay, for map T iteration, you just making some codes for each layers. Okay, for forward sequences, we just mathematically describe the situation. For intersections, original ABCD rectangle and the mapped horseshoe, you have the many intersections. We name them RK. Corresponding to the situation, this kind of the number history, we just symbolize S by S. So this up and down arrow as a marker, and from the here current situation, then this is the past situation. We just define the finite sequence, okay, and extend this situation for long time, infinitely many times. You just apply the T, then so infinitely many intersections corresponding to this situation. This infinite sequence corresponding S infinity. So many 0 and 1 symbols composed inside of the firstly you have firstly you have marker and 0, 1, 0, 1, 0, 1 something. Anyway, for forward time mapping sequence history are recorded. Okay, let's get the inverse time. Map inverse. Similarly, you can define the 0 and 1 situation. So in this situation, this horseshoe mapped once T is going to the ABCD rectangle. That means this horseshoe itself, T inverse. Similarly, repeating the inverse map for this structure, you have a history, similarly history, current here, and the past situation you just record here current, the past history you can memorize. And for backward sequences, you just define the rectangle and corresponding finite sequences like this. Here, marker. Sometimes it's called as a cursor. And for here, current situation and the past history, memorized for left-hand side, left direction. Anyway, it's corresponding to the cursor here and this kind of the finite sequence defined according to the rectangles. Okay. So just extension, infinitely many times, just repeat the mapping. Then you have infinite sequence like this. Okay. For example, 0, 1, 0, and then repeat sometimes, and ended by cursor. For backward sequences, we have this situation. Okay, combine them. Bidirectional invariant set you have. So according to this, you have a bidirectional infinitely long sequence you have. Intermediate situation, you have cursor, both hand for right, forward, for left hand side, backward. Okay, you have corresponding the very complex structure of the horseshoe structure. You have corresponding the sequence. Okay, and mapping T, we take consider the mapping T and sequence movement relationship. Now we have T inverse here. This horseshoe structure. This is T inverse. Map once T, then it's going to be ABCD rectangle. The left-hand side of the original T inverse situation, you have this infinite length of the symbol code. Here, press 1, press 0, because you have 0 position, T inverse, and mapped once. This situation happened. You can check the situation. This rectangle mapped to this portion by applying T. And for this situation, current position 0 for the right side of the cursor. So that 0 moves to the right 1 bit with this T. Similarly, you can check the situation. Portion 1 in the T inverse portion mapped by T, not T inverse. Mapped to T once, you just do this situation. The current position 1 going to the right 1 bit next position. Okay. That means by applying t for both position, both forward, backward position, map t is related to the 1-bit shift for the symbolic sequences. Okay, we define the shift map sigma. Sigma is the map from the infinite sequence to infinite sequence. Okay, according to T, the sigma is the shift map for the conventional existence symbol, mapping the once sigma just move all of the figures bit into the right side, 1 bit. So S -1 located here, just next to the marker, is going to 1 bit right side. This is the shift map. Then the dynamics T and the rectangles is rewritten in the sigma and infinitely sequences. It's corresponding contour set or a fractal or something. Okay, let me check the more concise examples. Okay, we just defined the basic sequence. 0 parentheses mean the repeating 0 infinity times, repeating infinite times. All bits are 0. If we apply the shift map sigma once to this sequence, all of them 0. Unchanged. Nothing changed. All bits are shift to right, but nothing changed. So with this sense, it's corresponding to the fixed point. Fixed point means x0 equal t x0. Apply the t to x0, you have x0 itself. Similarly, 1 basic sequence 1, apply the shift map once, you have still same sequences. Then there, period 1, fixed point. Okay. Similarly, let me check the 0, 1. Then you have this infinite sequences. Then once you just apply sigma for this, you have this. Applied once for sigma, for this sigma sequence, you have this situation. Just 1 bit shifted. Then this shifted sequence, once more apply the sigma, then original sequence you have. This is coincident to this original one. So it's mean the 2 periodic, period 2 motion. 0, 1, switch to 1, 0, and 0, 1 again. Okay? A homoclinic point and a heteroclinic point corresponding to the this kind of situation. And by taking shift mapping several times, you have fixed point itself or periodic points disappeared homoclinic points history. Okay, here comes the 3 periodic motion example. So you have this kind of repeat of the basic sequences. Period 3 motion. Okay, gray code can generate periodic patterns like this figure, like this table. So these sequences, basic sequence, repeat both sides of the backward and forward time, repeat many times, and making a periodic motion. But for example, if you have the 4-bit sequences, you can imagine the 2 power to 4. That means the 64-bit, 64. So 64 probability candidate, but it's only the several types of the periodic motion happened within the 4-bit pattern. Okay, in other words, very limited number of periodic points happen in the gray codes. Okay, here comes the example. You have 2 square situation for both forward and backward mapping. And we just name all of them like this sequences. So cross sections are intersections are actually the region. And if you put here, it's named the 0,1 and 0,1 position. Okay. Corresponding to this, we have the periodic motion possibly. Of course, as we seen here, 1,1 and 1,1,1,1 and 0,0,0,0 corresponding to the fixer point. Okay, let me check the situation. For example, if you have, okay, let me check the situation here. This is actually 0,1 right-hand side and left-hand side 1,1. Okay. And if you put the one, oh, excuse me, just inside of the area. 1,1 and 0,1. Okay, if you put here 1 and 0, you have some repeat patterns for both sides. Okay, just shift sigma once, then you have 1, 0, 1, and 1, 0, 1. That situation happened. Shift once more. 1, 1, right-hand side, 0, 0, 1, 1, and so on. One more applying sigma, you have original position. According to this, 0, 1, 0, here 0, 1 and 1, 0, left 0, 1, 0, 1 here, and 1, 0, 1, 0 here. Here. This is a new mapped point. Map here, sigma once. And 1, 0 and 1, 1. 1, 0 and 1, 1 here. So you have here. So this triangle means a period 3 motion. Okay. If you visualize the horseshoe map structure like this, then you find the periodic motion inside of the rectangle. This is the other examples. Yeah, actually, if you apply here, also shift mappings 3 times you have original position. So that means the period 3 motion. Once, twice, 3rd times you have original position. It's mean the period 3 motion. Okay. T square, excuse me, T cube, you just apply. Many intersections happen. According to the intersections, you can possibly find the periodic motion. And the 4th times you have the intersections is probably 256 intersections. According to them, you have many gray code periodic motions. Okay, for the Duffing equation. In fact, this situation happened for once mapping, and twice, and sometimes you have similar gray code, like anyway, the cross sections. Then all of them can sections are named by the codes, sequences, basic sequences, and the cross sections are candidate of the periodic points. For example, for 100 for the forward time and 100 for backward time, you have cross section here. It can be the candidate for periodic 3 motion if you can find the pattern. Okay, for Duffing equation, actually, like a schematic diagram, you have period 3 motion, for example, 2 types of periodic 3 motions, and 2 fixed point like this, or like this. All of them are unstable. All of them are unstable. Of course, it's these periodic points corresponding to the periodic orbit. We just do making the Poincaré mapping. We just sampled the points for this figure, but corresponding to the point, you have continuous periodic orbit. All of them are unstable. One of them we can stabilize. We just complete their chaos control. Okay, 4th time, t power to 4, t to power 4, almost the area very thin. Areas are very thin, almost a line. You can also check the combination of the forward time, the backward time sequences, and try to make a periodicity. This is another expression, representation of the finding the period 5 motion for t power to 4. Okay, you can find this kind of the repeating the shift map. You find the 5 periodic motion. In parallel, you have another pattern of the periodic motion in this horseshoe map structure. Okay. Again, this is the basic sequences pattern. Within the 8 periodic motion, you have totally some of them, many patterns happen. You can check the, you can pick one of them as them are typical UPOs. Of course, so many periodic motion. You can find if you track many long time and specify the rectangles. Okay. By using mapping sigma, you have the periodic points, all of them unstable. That situation, mathematically proven that with this horseshoe structure and the mapping sigma, then countably infinitely many periodic points exist inside of the horseshoe structure, and parallel, uncountable infinitely many non-periodic points embedded near the saddle, and dense orbit you can expect. We call them chaotic saddles. If you you cannot see any strange attractors, stable attractors, but possibly there exist the unstable chaotic saddles. All of them are unstable. If you put the initial point, probably finally the orbits far away, go far away, but chaotic saddles exist. Chaotic saddles exist near the saddle. Okay. For certain given differential equation, we just rigorously compute the UPP, unstable periodic point, by using a Newton's method or something. So you can horseshoe structure, you can find the candidate of the position of UPP, but it's only a candidate. Inside of the rectangle, you have unstable periodic point, but not accurate. So we just applied Newton methods to solve this equation. Sometimes you just TL. You can find the L periodical motion from the rectangle first guess. Certain probably this rectangle location information is good initial guess for the Newton method. Several updating can result the very accurate position of the periodic point. Okay, here comes the example. 5 periodic motion. Firstly, you just find the structure from this structure, the 00001 pattern. You have this 5 periodic motion candidate. Okay, area itself can be candidate, and we just focus on the homoclinic point as a first guess for Newton method. The Newton method can collect the information and can solve unstable periodic point, 5 periodic point from the homoclinic point initial guess. Similarly, next period 5 motion from the homoclinic point information. Also, you can specify the, for example, area information as the first guess. You can compute the anyway accurate UPP. Similarly, the other periodic points can be solved. Okay, here comes another example with same structure, 6 periodic unstable periodic point and corresponding unstable periodic orbit, unstable, but embedded inside of the horseshoe structure. 8 periodic, and so on. You just specified the number of period, and locate the roughly by tracking the manifold and the intersections, then Newton's method can solve the accurate position of location of the unstable periodic orbit. This is the first guess of the candidate. Then Newton's method can solve the accurate position of the UPP. This is the example eigenvalues, multipliers. So for fixed point data, you have, this is the instability, bigger than 1 into circle. So very unstable situation. So bigger period, instability increases. So 5 periodic motion, you have this instability, very, very unstable situation. But can be solved. Okay, now let us control all of them. If you located UPO corresponding to unstable periodic point, then we try to stabilize all of them by using external force control. The weak point of the OGY is updating timing. Each 2 pi or each period, you just to change the update control values, but it's very weak for the disturbances. External force control continuously fed the feedback control input into the system. It's very very high performance, very robust. We just applied the EFG to UPO. The control system signal flow seems to be very similar for the OGY method. And actually, this is the actual implementation. This is here, original differential equation, Duffing's equation, and apply the feedback values here. XT and YT are stored unstable periodic orbit time series. We just making the errors, evaluating errors, and just apply the control gain, KX and KY. We just apply here. And stabilize X star and Y star. Okay, this is the time series of the state X and control input UX. And here, just starting control. Without control, it makes chaotic motion for this example. And control start here. And very tiny, not tiny, comparatively big errors here as a control input, but stabilized period 1 motion. Period 1 motion here. Then turn off the control, it's going to be another attractor or chaotic attractors absorbed by the another attractors. Similarly, for 0-1 basic sequence, you can stabilize the period 2 motion, period 2 unstable periodic orbit, stabilized. Similarly, for period 3 motion, regularly period 3 motion you can realize with comparatively small or not small, I'm not sure, but stabilize the situation, 0 control input. Okay. for 8 periodic motion, you have this situation. Control input is very tiny and continuously 0 control input here. Turn off the control input, then it's going to be another attractor or chaotic attractor. Okay, now we just evaluate the control input with the logarithm scale. A very, very tiny control input remains. Here also, for 8 periodic motion, some very small corrections exist, but it's seems to be very small control input. Okay, for this EFC, the very tiny control signal remains. So, tiny, in that time, tiny means the stored target orbit keeps the very genuine UPO data. Okay. Okay, this is the phase portrait. If you enable the control with this initial point, it's quickly absorbed to the UPO orbit itself. This is the instability. Regardless this instability, it can be stabilized to the period 1 fixed point. Fixed and period 1 unstable periodic orbit. Okay, for this 0, 1, 2 periodic motion, if you put the initial point, any periodic initial point, it's absorbed to sticks to the 2 periodic motion, regardless of this bigger instability. Period 3 motion can stabilize. Also, period 8, very big instability orbit, but can be stabilized. And this check the robustness of the system. If you put periodically the disturbances like impulses, but correction very quickly realized and stick to the target UPOs. Okay, let me check the demonstration. Okay, here comes the uncontrolled motion, original Duffing equation responses. So almost to Hamiltonian situation, so very fully chaotic motion happen at that parameter value. Okay, firstly, enable the control quickly, very quickly stabilize the period 1, period 2 motion here. Or let me put the initial values, another initial values, other than like disturbances, but quickly stick to the 2 periodic motion for entirely state space. Very robust. Just to check this period 3 motion. Still very robust situation realized. And turn off the, if you turn off the control, it's going quickly absorbed by the chaotic attractor itself. Okay, turn on quickly realize the period 3 motion. This is mathematically guaranteed that there is this 3 periodic motion inside of this chaotic motion. Unstable, but stabilizable. Okay. Or period 8. Let me check the period 8. Very, very, very unstable situation, but stabilized by the control. And also you can check the robustness for this feedback control. Okay. Let's get back. All right. This talk is on based on this paper published last year. That's 2 years. Okay. And in this talk, our stance and unsolved problem are stated here. Firstly, excuse me. Firstly, the problem of the conventional controlling case is the targeting or locating the UPOs. Locating UPOs are very, very important, but unsolved, basically. But if you find the horseshoe structure for given dynamical system, you just specified mathematically exist UPO inside of the horseshoe structure. We just realized the control stabilization for the given UPOs. And if you have, anyway, a horseshoe structure, any number of periods UPO can be stabilized with this scheme. But if there is no horseshoe structure happen, probably degenerated cases or stable chaos attractor in general, probably no mathematically guaranteed UPOs happen inside of the chaos. This is the unsolvable problem. Okay, that is all for my talk. Okay, let me check the question if available. No question. That's I have no question available, received for now. But, okay. If you have any question on this talk, please send email to this email address. Okay, there is no question. Let me close my talk. Okay, thank you very much for attending this lecture.